Today in class we were talking about graphing quadratic inequalities, which was the last subject of the previous video. And I thought it might be helpful to do another video with another example. But this particular example has different results, and that's actually why I'm choosing this example. So if you remember from the previous video, we had an quadratic equation, and what we had before was less than 0. Now what we have is greater than 0. So it's a very similar problem, but it has some pretty different results. So there are two ways to solve this, and that is visually and algebraically. Now I haven't shown you the algebraic way yet, and I'm going to do that later in this video, and when you see the way I solve it algebraically, you're going to understand why I sort of shied away from it. The visual way is significantly easier. So let's go ahead and go into the visual way. In fact, that's the reason why I want to show you the visual way first, because that's the first one is probably going to be the one that you're going to do, and it's a lot easier. So visual way, the easy way. So the visual way, which is the easy way in parentheses. So let's scroll back up, because I want to keep this in mind. So we are looking for where the place. Let's not even think with the place yet. We're trying to find what values x could be that would make let's see, that would make x squared plus 5x plus 6 greater than 0. So we're just trying to find what possible values. I'm going to put a little bit of space there, just so we don't have too much stuff too close together. So we're trying to find what the possible values of x could be. So in other words, what are the values of x that's going to make this entire thing greater than 0? Okay, well, let's take a look at a related problem. So let's say we know that f of x equals x squared plus 5x plus 6. We know that f of x equals x squared plus 5x plus 6 is a parabola. We know that because of one of the previous videos. I don't remember which section number it is. I want to say it is 9.5. See, this is 9.6, so the section before, I believe, was when we graphed it. So we know from that section that this is going to be a parabola. It's a parabola because it has an x squared term in it. It doesn't have any x cubes. The highest power is x squared. So that tells us that it's a parabola. So that means it will look something like, this is not what it actually looks like, I'm just saying I have a general idea of what a parabola looks like. It looks vaguely something like this. This is more or less a parabola. I mean, not more or less, this is a parabola. But the point that I'm making is that while this is not actually a graph of this particular parabola, I just want to know what a parabola generally looks like. I don't need to actually graph this specific parabola to solve this. I can. If I wanted to actually graph the parabola to solve this, I can do that. I just don't really need to. And the reason why is because this is a parabola opening up, and this is a parabola opening up. So we're looking for the places where the parabola is greater than 0. We're looking for the places where this is greater than 0. So this, for all intents and purposes, is y. So where on the parabola is this going to be greater than 0? Well, we can see it's greater than 0 over here. We can see it's greater than 0 over here. So what are the x values for this? Well, it's going to be greater than 0 any place that's not between the x-intercepts. So let me explain it this way. The y value is greater than 0 when the x value, so the y value is greater than 0 when the x value is not between the x-intercepts. When it is between the two x-intercepts, it's going to be less than 0. We can see it here, it's going to be less than 0 here. So to find out where the y value is greater than 0, we find out where the x-intercepts are, and then we say it needs to be outside those x-intercepts. Okay, so let's go ahead. I'm going to clear this off. So I want to find the x-intercepts. Now that's kind of an abstract way to think of it. Not as abstract as the algebraic way, which we'll do later, but it's still pretty abstract. And it might take a while to wrap your head around it. Feel free to go back and watch it again. If there's still some confusion, you can ask me in class, and I will happily go over it again, maybe explain it in a different way. That might make it easier. But for now, let's go ahead and move on to finding these x-intercepts. Okay, so there's a few ways I can find the x-intercepts. I actually could factor this if I wanted to, but since we've been talking about the quadratic so much, I'm going to figure out I'm going to figure this out using the quadratic. So so let's find the x-intercepts. And let's I'm going to write off to the side here just because I don't want to lose it. We're talking about where x squared plus 5x plus 6 I've scrolled down so much that we're pretty far away from what the original problem was, so I wanted to write it over here in the corner just so we know what problem we're dealing with. So let's find the x-intercepts to this. If it were a function, to find the x-intercept to this. So let's go ahead and erase that. So we have x equals, and then we have negative b. So our b is going to be 5. So negative 5 plus or minus the square root of b squared. 5 squared is going to be 25 minus 4 times a is going to be 1, so I'm just going to leave that off if that's all the same to you, times c is going to be positive 6. So this is b squared, because this 25 is b squared, minus 4 times, I'll go ahead and just for the sake of completeness put the 1 in. So 4 times a is 1, times c is 6, and all over 2 times a. Now, in this case, I'm going to go ahead and just leave 2, because we have 2 times 1 is just going to give you 2. So, let's get rid of the extra stuff. So now we can go ahead and simplify this. And I will tell you now that we're going to get, in the end, 2 different whole numbers, but I still thought it'd be nice to practice this stuff, so we're still going to get negative 5 plus or minus square root of 25 minus 4 times 6 is going to give us 24, and still over 2. And let's go on to the next line. Equals, so we're still going to have minus 5 So we're going to have minus 5 plus or minus the square root of 25 minus 4 is going to give us 1. Still all over 2. And square root of 1, well, that's just 1. So we can say fraction of negative 5 plus or minus 1 over 2. This is going to give us that x is equal to, let's go ahead and do this individually. So negative 5 plus 1 is going to give us negative 4 over 2. So it's going to give us negative 2, or, because we're going to get two answers, one for the plus, one for the minus. Negative 5 minus 1 over 2, that's going to give us negative 6 over 2, which is going to give us negative 3. So negative 2 or negative 3 are the x-intercepts for the parabola. So, and I'm not going to, we don't need to graph the parabola in order to finish this, but I want to go ahead and just to drive the point home, show you exactly what I'm talking about. This means this is a parabola. It's going to be opening up because we have the exponent, the understood 1, in front of the x squared is positive. So this is going to be a pretty skinny parabola. It's going to go between, so it has x-intercepts of negative 2 and negative 3. So let's say this is negative 2 and this is negative 3, and I have no idea what the vertex is, but it doesn't matter because I don't need to know what the vertex is. But it's going to open up, so it's going to look something like this. It looks almost like that witch from Sleeping Beauty, but it works. So anyway, we're looking for where this is greater than 0. Well, it's going to be greater than 0 over here and over here. Now this is technically I'm combining two different graphs at once. This is combining a one-dimensional graph with a two-dimensional graph. That's the point that I'm getting at, is that this is where the y value is greater than 0, and this is where the y value is greater than 0. So let's graph this in a more, what's the word I'm looking for? In a more in a way that's an answer. So let's say I have the same program that I had before. I hope I'm, wow, what did I do? Oh, I did it in the wrong order. I know that you can't see it, so you can't see what stupid thing I did, but I'm going to fix it. Here we go. So this is going to be this is the graph of the of where this is greater than 0. Notice that you have an open circle because it's a strictly greater than, and an open circle here because for both cases it's a strictly greater than. So the parabola is going to be strictly greater than 0 from negative 3 exclusive, which means open circle, which means we don't actually include the 3, to negative infinity, and from negative 2 open circle to positive infinity. So this is the area, not area technically speaking, but this is the place where x is going to be greater than, is going to be, sorry, not x, where x squared plus 5x plus 6, we can call that equal to y if we want to. There's really nothing wrong with that. This is the place where y is greater than 0. Now I'm going to see if I can make this smaller, and I still want to keep it up here. See if I can make it always on top. So, oh good, it worked. And let's move a little bit to the left and try to shrink it a little bit more. Wow, that's getting kind of, you can still see it though. It still should make sense. Okay, so how can we describe this algebraically? Here, let me go ahead and erase this. I can describe this algebraically by saying that how can I describe this algebraically? Okay, I always have to double check to make sure I spelled algebraically correctly. It's strange to think of that as an adjective. So I can describe it algebraically by saying we want x is less than negative 3, but we also want to include, oops, I'm going to put a new line there. But we also want to include the places where x is greater than negative 2. So x is less than negative 3, or x is greater than negative 2. Now it's very important that I use or here, because I want to include this. This is the merging of the two individual graphs. So if I said x is less than negative 3 and x is greater than negative 2, well, list off for me a few numbers that are simultaneously less than negative 3 and greater than negative 2. Well, there are no such numbers. That doesn't really make any sense. So, what we have here then is this is the algebraic description of this graph right here. So we went ahead, the way we did this then is we found the graph and then came up with an algebraic description of that fits both of them. What if, on the other hand, we want to do it the algebraic way? And this is what I believe is the hard way. Okay, so I'm going to move that out of the way for now. And this way actually does not involve it, since it's not visual. We don't even picture it as a parabola. We don't even think of it as a parabola, and that's actually, in my opinion, what makes it kind of hard. Oh, and also I want to say this, the two of these together, this graph and this algebraic description, these are our two answers. Now you can actually, and I want to go ahead and do this, there's something called interval notation. It's not necessary to answer it this way, because this is just as good, but you're going to see interval notation in the next algebra class, and it may actually be required. I'm not sure. But I want to go ahead and expose you to interval notation. What I want to do is I want to find some way to describe from negative infinity to negative 3. So I'll say from negative infinity, crud, new line, I forgot. From negative infinity to negative 3. And this is kind of a side note. If your brain is full, then I've already shown you everything that is extraordinarily relevant. So we go from negative infinity to negative 3. So this interval notation, when we have this parentheses here, this means it's a strictly less than. This is an interval. This describes this part of the line. That's exactly what it's doing. It's just describing you're coming from negative infinity and you're going up to negative 3. Now we use a parentheses here for the negative 3 because we are not including 3. If this had been a solid circle, so this is just changing the problem. If this were a solid circle, which would mean this would be a less than or equal to, and this would be a greater than or equal to, then we would change this parentheses to a bracket. And the reason why I am not writing this out so intently is just because it's not going to be on the test. This is sufficient algebraic description for this particular class. May not be in the future though. Okay, so I changed it back to the parentheses just because that way we back to the original problem that we had. So now we want another way to describe this interval here. Well, it's remarkably similar. We can say that we go from negative 2 to positive infinity. And again, we use parentheses. Now, whenever we talk about infinity, you always use parentheses. You never use brackets because you can't include infinity. Okay, so I've described these two intervals right here. And so now I want to put them together. Well, remember we briefly talked about in the previous video that that is what we call the union of two different sets. So we can say that hope I get the coding right. Good. So it's this interval. I don't know why I erase that. So this interval union with this interval. So this tells us that we have negative infinity from negative infinity to negative 3, but we also have from negative 2 to positive infinity. And so also at the same time, let's say I'm going to draw this real quickly. We have from negative 1 to positive 1. Let's keep it real simple. That's negative 1 to positive 1. And this is our interval. Oh, no, that's not what I meant to do. That's well, that'll work, I guess. You might instinctively think, well, you'd use an intersection for this. Well, you could, technically speaking, but the most simplified form of this would actually just be negative 1 to positive 1. You don't need to put the positive 1 here. Technically, you probably don't need to put the positive infinity. Some teachers will want you to, some probably really don't care. Since this is not even necessary in my class, I obviously don't really care. But if you always need to put negative for negative infinity, though. So this is a description of negative 1 to positive 1. You could also think of this as an intersection of negative infinity to negative 1 intersectioned with 1 to positive infinity, but this is very far from the simplified form. This would be the most simplified form. Okay, so that's all of that involving interval notation is a sidetrack. I fully admit that. I just wanted to go ahead and show it to you because I wanted to expose it to you. So, or expose you to it, I should say. Okay, now I'm going to go ahead and clear off all of this and move this away. And I'm going to get rid of that interval notation for now. So, now let's solve this problem algebraically. Let's go ahead and I'm going to recopy what the original problem was. So the original problem was solving graph. Now I'm going to do it the algebraic way. Okay, so we start out with, we have that x squared plus 5x plus 6 is greater than 0. So what we're going to be doing is we're going to be doing some algebraic manipulations to get this in such a way that we can simplify it to the same answer that we got up here. We're going to end up with this same answer, but we're going to have a completely different method to do it. Now, again, this is the hard way. If by chance you find this easier, then that means that you're more of a symbolic thinker than a visual thinker, and there's nothing wrong with that. Actually, I kind of prefer the algebraic way just because my area of math that I deal with more frequently deals with more symbolic math than visual math. But if you're going into some kind of engineering or architecture, then you will much prefer the visual way. And of course, there's nothing wrong with either way. So let's go ahead and factor this out. Before I didn't factor it out, I just used the quadratic, but for this method we want to factor it out. So We'll factor it out by saying that x plus 2 times x plus 3 is greater than 0. All I did was I factored this into this. We have x plus 2 times x plus 3 equals 0. So here now is where we get into something that's kind of strange. A times b is greater than 0 when, now here's the strange part, a is greater than 0, not x, I wrote up an x. A is greater than 0 and b is greater than 0. Got the parentheses. Wait. Just a second. Let me write down this different way. Okay. It's probably seems strange that I have parentheses around this entire thing at first, but it'll come into play later. So, a times b is greater than 0 if a is greater than 0 and b is greater than 0. So let's think about what this means. If you have two numbers that are both positive numbers, like 2 times 3, that's a bad example because that's exactly what we have over here. Let's go 4 times 5. 4 times 5, well, I just start with the answer. 4 times 5, well, is going to equal 20, which is greater than 0. And it's greater than 0 because 4 is positive and 5 is positive. So a times b is going to be greater than 0 when a is greater than 0 and b is greater than 0. Because if you multiply two positive numbers together, you get a positive number. But there is another condition that will give us a product that is greater than 0. So, or, it's a times b is greater than 0 when a is greater than 0 and b is greater than 0, or a is less than 0 and b is less than 0. So what we have is, if you have two negative numbers, negative 4 times negative 5 will give you again positive 20 because the two negatives will cancel each other out. So if a and b are both greater than 0 or both less than 0, then a times b will be greater than 0. Okay, and now something that's very important is that we can't just mix and match these over here. These need to stay in the parentheses together, because you can't say that a is greater than 0 and a is less than 0. That doesn't make any sense. So we need to keep these separate, and then we will see when we apply this concept to this, we're going to see some very interesting things happening. So let's say that because we know that x plus 2 times x plus 3 is greater than 0, we can say that, so let me copy it down. We can say that x plus 2 is greater than 0 and x plus 3 is greater than 0, just like what we have over here. Or we can say simultaneously that x plus 2 is less than 0 and x plus 3 is less than 0. Now, I realized just a second ago that I said simultaneously when I didn't really mean that in a very technical sense. That probably didn't throw you off until I actually said that out loud, but I still thought I should point that out. Point being that either both of these are greater than 0 or both of these are less than 0. So now we can go ahead and solve these individually. So on the next line we'll have that if we want to continue solving this, I'm going to go ahead and I'm going to write for now I'm just going to keep it like this. So I'm going to go ahead on the next line, subtract 2 from both sides here. So we'll get that x is greater than negative 2 and x is greater than negative 3. and is part of the markup language that I'm using. So ignore that and I said a second ago. This is true, or we can subtract 2 from both sides here, and we'll get that x is less than -2, and x is less than -3. Close parentheses. Okay, so we have that x is less than -2 and x is greater than -2 and x is greater than -3. Well, where are both of those going to be true? So if we have that x is greater than -3, so if we have that x is greater than -2, so let's say we have 0. X is greater than 0 is greater than -2. And 0 is also greater than -3, because what we have is 2 lines. We have from -2 up to here, up to infinity, and we have from -3 up to infinity. So that means when we combine these two with and, we're only concerned about what they have in common, which is this, which is from -2 to infinity. So we can say from that that x is greater than -2. So we've simplified this entire expression down to x is greater than -2, because any time x is greater than -2, it's also going to be greater than -3. But that saves that the other way around. What if it's -2.5? Well, -2.5 is going to be greater than -3, but it's not going to be greater than -2. So x is greater than -2 and x is greater than -3 simplifies down to x is greater than -2. Okay, so at the same time over here, we can deal with, we still have this or in between, and we have that x is less than -2 and x is less than 3. So we have something very similar. We have that x is less than -2. I'm going to go ahead and draw it again. X is less than -2 and x is less than -3. So again, since we have this and here, we're looking for what they have in common. So it's going to be from -3 to -infinity, or to be completely technical, from -infinity to -3. So we can say that x is less than -3 covers x is less than -2, because if x is less than -3, it's going to be less than -2 also. So we could say that x is less than -3. So now we have two conditions: x is greater than -2, or x is less than -3. But wait a minute, let's go ahead and write that answer down, but then we'll see something pretty significant. X is greater than -2, or x is less than -3. So this is, oops, forgot to put that on a new line. So this is the answer that we have now, but that is the same that we had up here. Or we have it in a different order, but it still works out the same way. X is less than -3, x is less than -3, x is greater than -2, x is greater than -2. So now, without doing any graphing, any visual work at all, except for the individual graphs I did to show that this is equal to this, we've shown that x is greater than -2 or x is less than -3. So now, before we did the graph, we figured out what the algebraic form is. So now we can figure out, okay, where is x, if we want to graph it, where is x greater than -2 or smaller than -3? Well, we already graphed it because we did that in the previous problem. We have x is less than -3 or x is greater than -2. Okay, that concludes this example. If this last part, the algebraic way, you notice something kind of significant that's kind of unusual. The algebraic way may be harder. It's actually a lot shorter, though. That's part of the reason why I like it myself, because I mean, aside from the X Intercepts parts, I mean, we could have done that differently if you wanted to, but the visual way is easier because you see it as a parabola, because you see it, okay, this is definitely greater here, it's definitely less than here, so that's why I think the visual way is a little bit easier. If you don't understand the algebraic way, then do not feel bad, because this is really hard stuff. This is the hardest thing that I think that we have done in this class, and obviously you're not going to be required to do it this way. So really, the main reason I wanted to show it to you is just because I wanted to show you another way that it can be done. If you actually do prefer this way, that's fine. In fact, I'll be kind of impressed if you do this on the test, but I'm not. I would not expect it, just because, well, even I would probably, in fact, I know I would do this way if I was taking a test, because it's easier. And you know, when you're taking a test, you're not concerned about impressing anybody, you're concerned about getting it done. At least I am. Okay, that concludes this video. It turned out to be quite a bit longer than I thought it would be, but hopefully it will be helpful, and I will see you in, unless I make another Chapter 9 video, I'll see you in Chapter 11.